Hello all, welcome to this video on Operating System Lab. Today I'll be talking about FCFS scheduling in OS and its implementation in C. Let us see what scheduling is. CPU scheduling is the basis of a multi-programmed operating system. By switching the CPU among processes, the OS can make the computer more productive. The objective of multi-programming is to have some processes running at all times to maximize CPU utilization. Several processes are kept in memory at one time. When one process has to wait, the operating system takes the CPU away from that process and gives the CPU to another process. This pattern continues. Almost all computer resources are scheduled before use. Now let us see what a CPU I/O burst cycle is. The success of CPU scheduling depends on an observed property of processes. The process execution consists of a cycle of CPU execution and I/O wait. Processes alternate between these two states. The process execution begins with a CPU burst that is followed by an I/O burst, which is followed by another CPU burst, then another I/O burst, and so on. Eventually, the final CPU burst ends with a system request to terminate execution. The duration of CPU bursts have been measured extensively, although they vary greatly from process to process and from computer to computer. They tend to have a frequency curve as shown in the figure here. The curve is generally characterized as exponential or hyperexponential with a large number of short CPU bursts and a small number of long CPU bursts. This distribution can be important in the selection of an appropriate CPU scheduling algorithm. Now let us see about scheduling queues. As the process enter the system, they are put into a job queue which consists of all the processes in the system. The processes that are residing in main memory and are ready and waiting to execute are kept on a list called the ready queue. This queue is generally stored as a linked list. A ready queue header contains pointers to the first and final PCBs in the list. Each PCB or process control block includes a pointer field that points to the next PCB in the ready queue. The system also includes other queues. When a process is allotted the CPU, it executes for a while and eventually quits, is interrupted, or waits for the occurrence of a particular event such as the completion of an IO request. Suppose the process makes an IO request to a shared device such as a disk. Since there are many processes in the system, the disk may be busy with the IO request of some other process. The process therefore may have to wait for the disk. The list of processes waiting for a particular IO device is called a device queue. Each device has its own device queue. Now this is a queuing diagram representation for process scheduling. A common representation of process scheduling is a queuing diagram. Each rectangular box represents a queue. Two queues are used here, the ready queue and a set of device queues. The circles represent the resources that serve the queues and the arrows indicate the flow of process through the system. A new process is initially put into the ready queue. It waits there until it is selected for execution or is dispatched. Once the process is allotted the CPU and is executing, one of the several events could occur. The first one is the process could issue an IO request and then be placed in an IO queue. The process could create a new child process and wait for the termination of the child. And the process could be removed forcibly from the CPU as a result of an interrupt or be put back into the ready queue. In the first two cases, the process eventually switches from the wait state to the ready state and then is put back to the ready queue. A process continues this cycle until it terminates, at which time it is removed from all the queues and has its PCB and resources deallocated. Now, there are different types of schedulers. A process migrates among the various scheduling queues throughout its lifetime. The operating system must select, for scheduling purposes, processes from these queues in some fashion. The selection process is carried out by the appropriate scheduler. Often in a batch system, more processes are submitted than that can be executed immediately. These processes are spooled to a mass storage device like a disk where they are kept for later execution. The long-term scheduler or job scheduler select processes from this pool and loads them into a memory for execution. The short-term scheduler or CPU scheduler select from among these processes that are ready to execute and allocate the CPU to one of them. The primary distinction between these two schedulers lie in their frequency of execution. The short-term scheduler must select a new process for the CPU frequently. A process may execute for only a few milliseconds before waiting for an IO request. Often the short-term scheduler execute at least once every 100 milliseconds. Because of the short time between execution, the short-term scheduler must be fast. If it takes 10 milliseconds to decide to execute a process for 100 milliseconds, then 9% of the CPU is being wasted simply for scheduling the work. The long-term scheduler executes much less frequently. Minutes may separate the creation of one new process and the next. The long-term scheduler controls the degree of multi-programming, that is the number of processes in the memory. If the degree of multi-programming is stable, then the average rate of process creation must be equal to the average departure rate of processes. That is leaving the system. Thus, the long-term scheduler may need to be invoked only when a process leaves the system. Because of the longer interval between executions, the long-term scheduler can afford to take more time to decide which process should be selected for execution. It is important that the long-term scheduler selects a good process mix of IO bound and CPU bound processes. If all the processes are IO bound, the ready queue will almost always be empty and the short-term scheduler will have little to do. If all the processes are CPU bound, the IO waiting queue will almost always be empty, the devices will go unused, and again the system will be unbalanced. Some operating systems, such as time sharing systems, may introduce an additional intermediate level of scheduling, that is the medium term scheduler. The key idea behind a medium term scheduler is that sometimes it can be advantageous to remove a process from the memory and from the active contention for the CPU and thus reduce the degree of multiprogramming. Later, the process can be reintroduced into the memory and its execution can be continued where it left off. This scheme is called as swapping. The process is swapped out and is later swapped in by the medium term scheduler. Swapping may be necessary to improve the process mix or because a change in memory requirements has overcommitted available memory, requiring the memory to be freed up. Next is a dispatcher. This is another component that is involved in the CPU scheduling function. So this is the module that gives control of the CPU to the process selected by the short-term scheduler. It receives control in kernel mode as a result of an interrupt or a system call. The functions of a dispatcher are context switches, in which the dispatcher saves the state, which is also known as the context of the process or thread that was previously running. It then loads the initial or previously saved state of the new process. Next function is switching to user mode. Another function is jumping to the proper location in the user program to restart that program indicated by its new state. The dispatcher should be as fast as possible since it is invoked during every process switch. During the context switch, the processor is virtually idle for a fraction of time, thus, unnecessary context switches should be avoided. The time it takes for a dispatcher to stop one process and start another is called as dispatch latency. Now, this is a queuing diagram showing the addition of a medium term scheduling to the normal queuing diagram. Next is a context switch. When an interrupt occurs, the system needs to save the current context of the process running on the CPU so that it can restore that context when its processing is done, essentially suspending the process and then resuming it. The context is represented in the PCB of the process. It includes the value of the CPU registers, the process state, and memory management information. Switching the CPU to another process requires performing a state save of the current process and a state restore of a different process. This task is known as context switch. When a context switch occurs, the kernel saves the context of the old process in its PCB and loads the saved context of the new process scheduled to run. Context switch time is pure overhead because the system does no useful work while switching. Switching speed varies from machine to machine depending on the memory used, also the memory speed, the number of registers that must be copied, and the existence of special instructions such as single instructions to load or store all the registers. A typical speed is a few milliseconds. Context switch times are highly dependent on hardware support. For instance, some processors such as the Sun Ultra Spark provide multiple set of registers. A context switch here simply requires changing the pointer to the current register set. Of course, if there are more active processors than there is the register set, the system resorts to copying register data to and from memory as before. Also, the more complex the operating system, the greater the amount of work that must be done during a context switch. This is a diagram that is depicting the ready queue and various device queues. Next is preemptive and non-preemptive scheduling. CPU scheduling decisions may take place under the following four circumstances. The first is when a process switches from the running state to the waiting state, for example, as the result of an IO request or an invocation of wait for the termination of a child process. The second is when a process switches from the running state to the ready state, for example, when an interrupt occurs. The third is when a process switches from the waiting state to the ready state, for example, as the completion of an IO request. The fourth is when a process terminates. For situations 1 and 4, there is no choice in terms of scheduling. A new process, if one exists in the ready queue, must be selected for execution. There is a choice, however, for situations 2 and 3. When the scheduling takes place, under only circumstances 1 and 4, we say that the scheduling scheme is non preemptive or cooperative. Otherwise, it is preemptive. Under non preemptive scheduling, once the CPU has been allocated to a process, the process keeps the CPU until it releases the CPU either by terminating or by switching to the waiting state. This scheduling method was used by Microsoft Windows 3.x. Windows 95 introduced preemptive scheduling, and all subsequent versions of Windows operating system have used preemptive scheduling. The Mac OS X operating system for the Macintosh also uses preemptive scheduling. Previous versions of the Macintosh OS relied on cooperative scheduling. Cooperative scheduling is the only method that can be used on certain hardware platforms because it does not require the special hardware, for example, a timer, needed for preemptive scheduling. Unfortunately, preemptive scheduling can result in race conditions when the data are shared among several processes. Consider the case of two processes that share data. While one process is updating the data, it is preempted so that the second process can run. The second process then tries to read that data which is in an inconsistent state. Preemption also affects the design of the operating system kernel. During the processing of a system call, the kernel may be busy with an activity on behalf of a process. Such activities may involve changing important kernel data, for instance, IO queues. What happens if the process is preempted in the middle of these changes and the kernel or the device driver needs to read or modify the same structure? Chaos ensures. Certain operating systems, including most versions of Unix, deal with this problem by waiting either for a system call to complete or for an IO block to take place before doing a context switch. This scheme ensures that the kernel structure is simple since the kernel will not preempt a process while the kernel data structure are in an inconsistent state. Unfortunately, this kernel execution model is a poor one for supporting real-time computing where tasks must complete execution within a given time frame. Next is the scheduling criteria. In choosing which algorithm to use in a particular situation, we must consider the properties of the various algorithms. Which characteristics are used for comparison can make a substantial difference in which algorithm is judged to be the best. The criteria include the following: CPU utilization. It indicates the amount of load handled by individual processor cores to run various programs on a computer. We want to keep the CPU as busy as possible. Conceptually, CPU utilization can range from 0 to 100%. In a real system, it should range from 40% for a lightly loaded system to 90% for a heavily loaded system. Next is throughput. If the CPU is busy executing processes, then the work is being done. One measure of work is the number of processes that are completed per unit time, called throughput. For long processes, this rate may be 1 process per hour. For short transactions, it may be 10 processes per second. Next is the turnaround time. The interval from the time of submission of a process to the time of completion is the turnaround time. It is the total time taken to execute a process from the moment it enters the CPU until it completes the execution, including both the CPU processing time and any time spent waiting in the ready queue or waiting for IO operations. Now, this can be calculated as turnaround time is equal to completion time minus arrival time. Next is the waiting time. It is the sum of the periods spending waiting in the ready queue. This is the difference in time between turnaround time and burst time. Then there is response time. In an interactive system, turnaround time may not be the best criterion. Often, a process can produce some output fairly early and can continue computing new results while previous results are being output to the user. Thus, another measure is the time from the submission of a request until the first response is produced. This measure, called response time, is the time it takes to start responding, not the time it takes to output the response. The turnaround time is generally limited by the speed of the output device. Some of the other important terms include the arrival time, which is the time at which the process arrives in the ready queue. Then there is the completion time, which is when a process finishes execution and is no longer being processed by the CPU. It is the summation of the arrival, waiting, and burst times. It is an essential metric in CPU scheduling as it can help determine the efficiency of the scheduling algorithm. Then there is the burst time, which is the time required for a process for CPU execution. Now, what is a scheduling algorithm? In computing, scheduling is the action of assigning resources to perform tasks. The resources may be processors, network links, or expansion cards. The tasks may be threads, processes, or data flows. The scheduling activity is carried out by a scheduler. Scheduling is fundamental to computation itself and an intrinsic part of the execution model of a computer system. Now, some of the goals of computing using a scheduling algorithm: maximizing throughput, minimizing wait time, minimizing latency or response time, and then maximizing the fairness. That is, equal CPU time to each process, or more generally, appropriate times according to the priority and workload of each process. In practice, these goals often conflict. For example, throughput versus latency. Thus, a scheduler will implement a suitable compromise. Preference is measured by any one of the concerns mentioned above, depending upon the user's needs and objectives. In real time environments such as the embedded systems for automatic control in industry, for example, robotics, the scheduler also must ensure that the processes can meet deadlines. This is crucial for keeping the system stable. Scheduled tasks can also be distributed to remote devices across a network and managed through an administrative backend. Now we will see FCFS scheduling algorithm, which is first come first serve. Now this is the simplest CPU scheduling algorithm. With the scheme, the process that requests the CPU first is allocated the CPU first. The implementation of the FCFS policy is easily managed with a FIFO queue. When a process enters the ready queue, its PCB is linked onto the tail of the queue. When the CPU is free, it is allocated to the process at the head of the queue. The running process is then removed from the queue. The code for FCFS scheduling is simple to write and understand. On the negative side, the average waiting time under the FCFS policy is quite long. Consider the following set of processes that arrive at time 0 with its process length given as 24, 3 and 3, which is for the processes P1, P2 and P3. Now, if the processes arrive in the order P1, P2, P3 and are served in FCFS order, this is the resulting Gantt chart. Now, a Gantt chart is a horizontal bar chart that is used to show CPU scheduling in graphical view that help to plan, coordinate and track specific CPU utilization factors like throughput, waiting time, turnaround time, etc. Now we'll see, according to that Gantt chart, the waiting time for process P1 is 0, P2 is 24 and P3 is 27. So the average waiting time will be these three values added together divided by 3, which is 17 millisecond. Now if the process was arriving in the order P2, P3 and P1, this will be the resulting Gantt chart. Now here the waiting times are 0, 3 and 6. So the average waiting time will be adding these values together divided by 3, which is 3 millisecond. This reduction is substantial. Thus, the average waiting time under an FCFS policy is generally not minimal and may vary substantially if the process CPU burst times vary greatly. FCFS scheduling algorithm is non-preemptive. Once the CPU has been allocated to a process, that process keeps the CPU until it releases the CPU either by terminating or by requesting IO. The FCFS algorithm is thus particularly troublesome for time sharing systems where it is important that each user gets a share of the CPU at regular intervals. It would be disastrous to allow one process to keep the CPU for an extended period. Since context switches only occur upon process termination and no reorganization of the process queue is required, scheduling overhead is minimal here. Next is convoy effect. Consider the performance of FCFS scheduling in a dynamic situation. Assume that we have one CPU bound process and many IO bound processes. As the processes flow around the system, the following scenario may result. The CPU bound process will get and hold the CPU. During this time, all the other processes will finish their IO and move to the ready queue, waiting for the CPU. While the processes wait in the ready queue, the IO devices are idle. Eventually, the CPU bound process finishes its CPU burst and moves to an IO device. All the IO bound processes which have short CPU burst are executed quickly and move back to the IO queues. Now, at this point, the CPU sits idle. The CPU bound process will then move back to the ready queue and be allocated to the CPU. Again, all the IO processes end up waiting in the ready queue until the CPU bound process is done. There is a convoy effect as all the other processes wait for that one big process to get off the CPU. This effect results in lower CPU and device utilization than might be possible if the shorter processes were allowed to go in first. Now, here there is no starvation because each process gets a chance to be executed after a definite time. The turnaround time, waiting time, and response time depend on the order of the arrival of the process and can be high for the same reasons above. No prioritization occurs since this system has trouble meeting the process deadlines. The lack of prioritization means that as long as every process eventually completes, there is no starvation. In an environment where some processes might not complete, then there can be starvation. This algorithm is based on queuing and it also favors CPU bound processes than IO processes. Now, the time and space complexity for FCFS. The worst case and average case time complexity will be theta of n square. The best case time complexity is theta of n and space complexity is theta of n, where n is the number of processes. Now we'll see the logic of the program that I'm about to implement. So in this program, first it will ask for the number of processes and will collect details regarding each process like the arrival time and burst time. Then the processes are sorted based on the arrival time. So in the program itself, there will be a logic to add on process numbers as soon as details of each process is entered in the system. So if the arrival time is the same, then the process with that lower number will be processed first. Then the calculation of completion time, turnaround time and waiting time will be done. Then the average of waiting time and turnaround time will be calculated and finally the Gantt chart of this execution will be printed. Now this is an example showing the same. So throughout this experiment, the assumption is that there is no IO burst time or there is no context switch overhead here. Now we have a set of 5 processes P0 to P4 and its arrival time and burst time is given in the question. So from those values we'll be able to calculate the start time, completion time, turnaround time, wait time and response time. Now with the details available in the question, we'll construct a Gantt chart like this. So from this we'll be able to fill in the details that is given here. So the start time of each process can be seen on the Gantt chart. For P0 it's 4, P1 it's 13, P2 is 0, P3 it's 17 and P4 it is 9. Then the completion time will be 9 for P0, 17 for P1, 3 for P2, 19 for P3 and 13 for P4. Then there is the turnaround time. So turnaround time is obtained by completion time minus arrival time. So the values will be 5, 11, 3, 13 and 8. Then there is the wait time. So the wait time will be calculated using the equation turnaround time minus the burst time. So here there is only CPU burst, there is no IO burst. So waiting time, turnaround time minus the burst time. So the values will be 0, 7, 0, 11 and 4. Then there is the response time. Response time will be the difference between start time and arrival time. So values will be 0, 7, 0, 11 and 4, which is same as that of waiting time in this case. From those values we can calculate the average response time. So we'll take these 5 values and divide them by 5. We'll get the value 4.4. Then we have the CPU utilization, whose equation is total time minus idle time divided by the total time multiplied by 100. So the total time taken is 19. The idle time here is 1 unit. So the value will be 94.73. Then the throughput is calculated by the total number of processes divided by the schedule length. The schedule length is calculated by the maximum completion time subtracted with minimum arrival time. So here the values will be 19 and 0. 5 divided by 19 will be 0.263. So these are the equations that we used for the calculation. Now this is the program that was implemented based on the logic we discussed before. For the output, I have used two cases. This is the case of the 3 processes we have discussed as an example when we discussed the FCFS algorithm. So there is no idle time in this case. So after entering these arrival and burst time, we'll get this chart with the completion time, turnaround time and wait time and the Gantt chart, and finally the average turnaround time as 27 and average waiting time as 17. Now this is another case where there is a unit of idle time. The same example we used for the calculation of different parameters just before. So here you can see that the answers are in the same format except that here we'll have an idle time. Now in this case, the average turnaround time is 8 and the average wait time is 4.4. Now we'll see a demo of this program. So we have the code OS FCFS.c here. It is the same program that I discussed in the PowerPoint presentation before. Now we'll compile the program using the GCC command gcc osfcfs.c. Now the compilation is fine. Now we'll run the program. And here we'll give the set of 5 processes. It's the first case, and the combination of arrival and burst time as 4, 5, 6, 4, 0, 3, 6, 2 and 5, 4. This is a case where we have 1 unit of idle time with the average turnaround time and wait time. The second case, we are giving the number of processes as 3. So there we have the combination 0, 24, 0, 3 and 0, 3. There also we have calculated the wait time and the average wait time and average turnaround time. That's all for now. Thank you for watching.